Hello, welcome to Unit 7, Lesson 22, Rewriting Quadratic Expressions in Vertex Form. The learning objectives for this lesson are to be able to identify the vertex of a graph of a quadratic function when the expression that defines it is written in vertex form, to know the meaning of the term vertex form, and can recognize examples of quadratic expressions written in this form. And then when given a quadratic expression in standard form, you will be able to rewrite it in vertex form. So as you can tell, we are focusing on vertex form. Now, prior to this unit, we did spend a little bit time on vertex form. So just a reminder, vertex form is where you have y equals a times x minus h squared plus k. And you can pull the vertex from that by doing the opposite of h and then the k value. So that is your vertex. Just a reminder, the vertex is either the most maximum point or the most minimum point, depending on if it opens up or if it opens down. If it opens up, it's a minimum point. If it opens down, it is a maximum point. So let's go ahead and take a look at the warm-up. So it says these expressions each define the same function, x squared plus 6x plus 8, and then x plus 2 times x plus 4, and then x plus 3 squared minus 1. Without graphing, it wants you to determine where the following features would be on a graph that represents the function. So to determine the vertex, I'm going to look at the one that's in vertex form, which is the last one. So I can see, remember, I'm going to do the opposite of what's inside the parentheses, so that's -3, and then the same of what's outside the parentheses, which is -1. So my vertex is going to be -3, -1. For my x-intercepts, I'm going to look at factored form. And I know I'm just going to take the opposite of these. So my x-intercepts are -2, 0, and -4, 0. And then finally for the y-intercept, I do need to use standard form, which is the first expression. And that's just the c value. So in this case, the y-intercept is 0, 8. All right, let's take a look at activity 2. All right, in this next activity, we're going to be going back and forth between vertex form and standard form. So let's take a look at question 1. It says, here are two expressions in vertex form. Rewrite each expression in standard form and make sure you show your reasoning. So go ahead, pause the video, and work on A and B. All right, so for A, I know x plus 5 squared is going to be x squared plus 10x plus 25, and then I have to add that one. So I have x squared plus 10x plus 26. For B, I know I'm going to have x squared minus 6x plus 9, and then I have to minus 7. So that's x squared minus 6x plus 2. So remember our shortcut for changing perfect squares from factored form to standard form. I know that this number right here is going to be made up of 2 times 5, whereas this number here is going to be made up of 2 times 3. So just keep that in mind for when you're creating a perfect square in standard form. Question 2 said to think about the steps you took and about reversing them. It says try converting one or both of the expressions in standard form back into vertex form. Explain how you go about converting the expressions. So go ahead, pause the video, and see if you can do this on your own. All right, I'm going to focus on the first one. I'll actually do both of them so you can see, but let's say you did the first one. So x squared plus 10x, I forgot my x. Plus 26. So to put it back in vertex form, I can complete the square by subtracting 1 from that expression. So if I subtract 1, it would look like this. So x squared plus 10x plus 25, but I still need to include the 1 because I can't just get rid of it, right? We need to make sure that our expression stays, the value of the overall expression stays the same and doesn't change. So instead of writing it as 26, I'm just going to write it as 25 plus 1, right? 25 plus 1 is 26. I have my perfect square part of the expression, and then I have my plus 1. Now that I have my perfect squared, I can factor this and rewrite it as a factored squared. So this is just x plus 5 squared, and then I bring down my plus 1. Same thing for x squared minus 6x plus 2. If I want to make this a perfect square, I do need to have a 9 in here. So if I think about, okay, well, how can I make 2 into a 9? I know that I need to add 7 more. So when I add 7 more, I do end up with my x squared minus 6x plus 9. But again, I can't just get rid of that 7 and just call it a day. I need to still show that that 7's there. And I do that by doing 9 minus 7, right? 9 minus 7 equals 2. So I'm not changing the overall value. I'm just rewriting 2 as 9 minus 7. Here's my perfect square part of the expression, so I can rewrite that as x minus 3 all squared minus 7. All right, let's take a look at the next problem. So number 3 says to test your strategy for rewriting x squared plus 10x plus 9 in vertex form. So again, pause the video, see if you can do this on your own and what you come up with. All right, so think of your perfect squared. What does 9 need to become in order to have a perfect square? Well, this 10 is made up of 2 times 5. So that means in order to make this a perfect squared, I need the 9 to become a 25. So I look at it that way. So now, though, I still need to keep in mind that I did something to get that 25, and in this case, I added 16, right? So that means I can rewrite 9 as 25 minus 16. My perfect squared part of the expression is just x plus 5 squared, and then now I bring down the minus 16. So let's check the expression you rewrote in vertex form. So using your graphing technology, graph both the x squared plus 10x plus 9 and your new expression. Does it appear to define the same function? If you convert your expression in vertex form back to standard form, do you get x squared plus 10x plus 9? So go ahead, graph both the standard form and the vertex form that we got in question 3. Graph both of those and see if you come up with the same graph. And then also go ahead and try converting the expression we got for number 3 into standard form to make sure it works out. So hopefully you saw that the graphs were actually the same. And let's go ahead and show what converting back into standard form would look like. So x plus 5 squared is just x squared plus 10x plus 25 minus 16. And then 25 minus 16 is 9, so we end up with x squared plus 10x plus 9. So the key thing to remember from this activity is that whatever you do to the standard form expressions to complete the square, it's important that you do not change the value of the expression. So, for example, in number 3, we recognize that to change 9 into 25, I have to add 16. But I can't just add 16 and call it a day. I do have to think of it as how can I rewrite 9 so that there's a 25 involved. And I can do that by doing 25 minus 16. So just remember that's a really key part to this strategy. All right, let's take a look at the next activity. All right, so I want to share some expressions with you. So we have 3x squared plus 12x plus 9, negative 2x squared minus 4x plus 6, 4x squared plus 24x plus 20, and then negative x squared plus 20x. So these are some other expressions that you could rewrite in vertex form to help us identify the vertex of the graph. So I want you to think about at least one thing you notice about these four expressions and one thing you wonder. So go ahead, pause the video, and try to think of something you notice and something you wonder. So some things you may notice is that in all the expressions, the coefficient of the squared term is not 1. Hopefully you notice that. Also, you may have noticed that each of the expressions contains terms that have a common factor. You may have also noticed the coefficients of some squared terms are negative, so there are a couple negatives. And maybe you notice that the last expression has no constant term. Some things you may wonder is, well, how do we write these expressions in vertex form, right? We've focused so far on expressions that the leading coefficient is 1. We haven't done anything where the coefficient is not 1. And then you also may wonder whether it is still possible to write the last expression in vertex form given that it has no constant term. So let's take a look at the first question. It says, here's one way to rewrite 3x squared plus 12x plus 9 in vertex form. Let's study these steps, and we're going to write a brief explanation of what's happening in each step. So the first step they did was they rewrote it as 3 times x squared plus 4x plus 3. So it looks like they factored out the 3, right? They divide every term by 3, and then they brought the 3 outside to the parentheses. And then they rewrote the expression as x squared plus 4x plus 3 plus 1 minus 1. So here, what they did was they recognized in order for this to be a perfect square, this needed to be a 4. So to do that, they added 1, but then they also subtracted 1 to not change the value of the expression. So they add 1 to complete the square, and then subtract 1 to keep the value of the expression the same. Okay, let's look at the next one. They went from 3 plus 1 to 4, so they combined, let's separate it like this, combined 3 and 1 to make 4. And then they rewrote the expression x squared plus 4x plus 4 as x squared plus 2. So they rewrote x squared plus 4x plus 4 as a squared expression. And then last but not least, they ended up with 3 times x plus 2 squared minus 3. So looks like they redistributed the 3. Now, notice when you redistributed the 3, you didn't actually put it inside the x plus 2 parentheses. It just stays out in front because what you're doing is you're multiplying 3 by that whole factor, not by each individual term inside that factor. So just be very careful. All right, so now go ahead and answer the questions B and C. So B talks about what is the vertex of the graph, and what does the graph open up or down, and how you know. All right, so for B, remember we take the opposite of what's inside the parentheses, so that's -2, and then the same for what's outside, so that's -3. So our vertex is -2, -3. And then we know this opens up because we see that the A value, which in this case the A value is this number right here, is a positive number. If it was negative, then it would open down. All right, let's take a look at the next question. So question 2 now wants you to rewrite each expression in vertex form. Make sure you show your reasoning. So go ahead, pause the video, and try to follow based on the steps in the previous question to rewrite this in vertex form. All right, let's take a look. So the first thing I'm going to do is I'm going to factor out the -2. So now I have x squared plus 2x minus 3. To make this a perfect squared, I need this to become a positive 1. So to make -3 into a positive 1, I need to add 4. But so I don't change the value of my expression, I'm also going to subtract 4. In doing that, I now have x squared plus 2x plus 1 minus 4. I can now rewrite this one as a perfect square. So now I have x plus 1 squared, and then I bring down my minus 4. And then I'm going to redistribute my -2. So I have -2 times x plus 1 squared plus 8. All right, let's try B. So for B, I'm first going to factor out the 4. So I have x squared plus 6x plus 5. In order to make this a perfect squared, I need this to become a 9. So that means I need to add 4, but I can't just add 4 because that would change the value of my expression. So I'm also going to subtract 4. So now I have x squared plus 6x plus 9 minus 4. I can rewrite my perfect square in factored form. So that's x plus 3 squared minus 4. And then redistribute my 4. So I have 4 times x plus 3 squared minus 16. Okay, last one. Factor out my -1. So I have x squared plus 20x minus 20x, sorry, not plus 20x. So in order to make this a perfect squared, I do need a positive 100 because this is 2 times 10, and 10 squared is 100. So I'm going to add in 100, but again, we need to make sure we also subtract 100 so we don't change the value of the expression. I can rewrite my perfect square in factored form. So that's x minus 10 squared minus 100. And then redistribute my -1. So I have negative x minus 10 squared plus 100. So one thing I want to point out here with number 2 is that you may have factored out 2 instead of 4, because 2 also does work, but 4 is going to be the better factor to use because it does allow the squared term to have a coefficient of 1, which makes it easier to complete the square. If we use 2, the squared term still has an inconvenient coefficient, and that is neither 1 nor a perfect square, so it makes it a little bit more difficult to complete the square. And then just also remember, you can check to make sure you are putting these in vertex form correctly by rewriting them in the original expression. So just a reminder, we focused on several different forms of quadratic expressions, and each form has its benefits. So standard form is great for finding the y-intercept. Factored form is great for finding the x-intercepts, and vertex form is great for finding the coordinates of the vertex. Ideally, at this point, you should be able to transition between each of the forms. The only one that you may not be able to do is factored form, especially if there are irrational factors or irrational x-intercepts. But if we do have whole number or integers, I should say, intercepts, then you should be able to go from standard to factored, factored to standard, and then also vertex to standard and standard to vertex. Remember, if you have a coefficient other than 1, one of the things you should do to make it easier is to factor out that coefficient if you're able to. Sometimes you won't be able to. So for example, negative 3x squared plus 24x minus 36, we can factor out a negative 3 to make it as x squared minus 8x plus 12. Okay, this is going to be much easier to complete the square and to put it into, to complete the square and put it back into vertex form. It's also much easier to factor, so my recommendation to you is whenever you're dealing with quadratics, look to see if they all have a common factor first. All right, that's it for today's lesson. Thanks for watching.